So this is a lesson on atoms. Atoms were first discovered, hypothesized by the ancient Greeks in maybe the 5th century BC. Philosophers Leucippus and Democritus um, suggested that there was a minimum size for matter. Democritus coined the word atomos, which derived from the Greek word for uncuttable or indivisible. So the idea was that there's some smallest size for things. That's a kind of a crazy idea. It ends up being true. But if you think about an ocean of water, and you think about a lake of water, and you think about a pond of water, and a pool of water, and a cup of water, and a drop of water, and a droplet in a mist, water maintains basically its same properties over an enormous range of sizes. And to think that there's some minimum size for water, where if you go below that size, it's not water anymore, was a radical idea for scientists and been bandied around for a long time, as you can see here. Western science sort of came up with it again in the 1600s, I think. And so we can see that the first suggestions of atoms were in the 5th century BC that we know of. Later, Aristotle and others believed that matter consisted of various combinations of the 4 elements. You've probably heard of this before: earth, air, fire, and water. And then in 1807, an English school teacher named John Dalton proposed his atomic theory. And this is the one that the last time which it eventually stuck. It was just a theory. There weren't really convincing scientific arguments until 100 years later, maybe, something like that. So here's Dalton's atomic theory in 5 postulates. Matter is composed of exceedingly small particles called atoms, and atoms is the smallest unit of an element that can participate in a chemical change. It's pretty good for 1807. An element consists of only one type of atom. The elements are the things we have in the periodic table, which you've probably seen in a science class somewhere. And we'll see it again shortly. Which has a mass that is characteristic of the element, and is the same for all elements, all atoms of that element. All atoms of a given element, like hydrogen or iron or gold or uranium or lithium, are all identical to each other within a given element. I'm going to have to hedge on that a little bit later on when we talk about isotopes. Atoms of one element differ in properties from atoms of all other elements. A hydrogen atom is not like a helium atom or like a gold atom. A compound consists of 2 or more elements combined in a small whole number ratio. And so we'll talk about compounds, or we have actually talked about compounds. So H2O is water, and that's a compound. NaCl is a compound. In water, there are always 2 hydrogens for every oxygen. In CO2, there are 2 oxygens for every carbon. We saw sucrose last time, which was C12H22O11. Right? Sucrose would always have the elements in that ratio. Atoms are neither created nor destroyed during a chemical change, but instead rearranged to yield a different type of matter. When we burn gasoline, it takes these hydrogen and carbon chains and combines them with oxygen out of the atmosphere and converts that into carbon dioxide and water, CO2 and H2O. So this was Dalton's atomic theory from a long time ago. Here are some examples. If you get a penny before 1981, they're 100% copper. The later ones have zinc in them, I believe, and in fact just a thin layer of copper on the outside. But pre-1981 pennies are 100% copper and each contains about 3 times 10 to the 22nd copper atoms. That's a 3 with 22 zeros after it. I do not know the name of that number, but it's a lot. We'll go with a bajillion. Dalton's atomic theory provides a microscopic explanation of many macroscopic properties that you've learned about. If atoms are neither created nor destroyed during a chemical change, then the total mass of matter present when matter changed from one type to another will remain constant. And so you can see these two pictures. You know, if you have 2 larger green atoms plus 2 smaller blue atoms, and they recombine in the way you see on the right, you can see the total amount of matter is the same. Those 2 on the left may look very different from the 2 on the right, but the total mass is the same. They may look, it's like combining iron and oxygen, right, and then producing iron oxide. The 2 on the left have their own properties, and the 2 on the right have their own properties. And obviously, you can come up with much more complicated versions than we're showing there. The law of definite proportions, or the law of constant composition, states that all samples of a pure compound contain the same elements in the same proportion by mass. That's just what I was saying. If H2O has 2 hydrogens for every oxygen, you can change that into a mass statement. One oxygen actually has about 8 times the mass of the 2 hydrogens, and those ratios will remain constant. So we can ask the question, what are atoms composed of? In the early 20th century, J.J. Thomson put a large voltage on a metal and noticed that a beam of charged particles came off. He could see them because he aimed the charged particles at a target, a phosphorescent surface, and it glowed as these particles came off. Further experiments allowed him to determine the ratio of the particles, these particles that were coming off, the ratio of their charge to their mass. It doesn't really matter the details of that, but he was taking metals and he was basically just putting a large voltage on them, and they were shooting off what we now know to be electrons. And so they knew that these particles that were coming off were somehow part of the atoms that made up the iron. And so these were early clues that atoms were not just indivisible particles, but were composed of even smaller particles. Those particles, of course, no longer carry the property of the element. If you pull an electron off a hydrogen atom, it no longer acts like a hydrogen atom. It's just an electron running around somewhere. In the same way that, if you pull a brick off a house, it's just a brick now. It's not part of that house anymore. So after J.J. Thomson came along, an American named, J.J. Thomson was English, an American named Robert Millikan performed what we call the oil drop experiment. What he did was he sprayed, we'll see a picture of this in a second, he sprayed oil droplets through a mister to make like a mist of oil droplets, and then he used a voltage to sort of balance them. When you spray something in a mist, it charges it like if you rub your shoes on the carpet. And then he was able to assess how much charge was on it by putting an electric field on it. Let me see if I can draw a picture of this. So here's the idea. You set up a little plate here, like this, right? And what you do is you take a battery and you put the positive end of the battery on the top. You put the negative end of the battery on the bottom. And then you send little oil particles in here. You just have a mist that just sprays them in there. So you get these little oil particles in there. And just the friction of shooting out the oil particles gives them a net charge. Maybe a little negative charge here and there. Maybe there are a couple of negative charges on some of the drops. These are droplets, so they're gigantic compared to the size of an atom. And so you might have some with 3 charges, some with 1 charge and stuff. Well, he could adjust the voltage here. We know that negatives are attracted to positives, right? And so all of these guys would be attracted to this top plate, but gravity is pulling down on them. And so he could tune the voltage on this plate and figure out what voltage would balance the weight, and that allowed him to determine what the charge was on each one of these atoms, on each one of these droplets of oil. This is an experiment that physics majors redo all the time. It's pretty easy to do. Some old experiments are really hard to do, but some are pretty easy, and this is an easy one. And what he noticed was that all of these oil droplets had a charge that was an integer multiple of a specific number. And so that number was 1.6 times 10 to the minus 19th coulombs. You can kind of see it down here. And so he figured out what the charge was, and then he used J.J. Thomson's charge to mass ratio, which he figured out, to get the mass. And so the charge on an electron is 1.6 times 10 to the minus 19th, that should be an exponent there, times 10 to the minus 19th coulombs, and its mass was this. And so this was our first subatomic particle, the electron, the first one humans sort of figured out. And we knew what its charge was. It's technically got a negative charge, and its mass is 1.9 times 10 to the minus 31 kilograms. That's a teeny, teeny, tiny mass, right? There's 30 zeros, there's a decimal point, and then 30 zeros before you get to the 9. That's a shockingly small number. Here's another picture of his experiment, and you can kind of see he had all these oil droplets in here, and he was using his apparatus to balance the electric field with the gravitational force and stuff like that. And then he was finding these numbers, and if you look at these numbers, all these numbers, 4.8 times 10 to the minus 19, 3.2 times 10 to the minus 19, 6.4 times 10 to the minus 19, 1.6, and so on, they were all multiples of 1.6 times 10 to the minus 19, and so this is what he determined had to be the charge on an electron. It was a clever experiment. So what else is in an atom, right? That's the next question. What else is in there? And so an Australian named Ernest Rutherford, working in England, I believe, did another experiment in which he said, well, okay, now we've got these electrons. There has to be positive charge in an atom also, because atoms are neutral on their own. And so he started firing these little particles called alpha particles that they had found. It ends up being just a helium nucleus, pieces of gold foil. And these alpha particles are positively charged, and it's like shooting bullets at it, basically, these alpha particles. And he wanted to see what would happen. And so, let's look at this next picture. And so here's what he did. This is a beam of alpha particles coming through here. We don't have to figure out how he did that. This little yellow box here is a piece of gold foil, and he wanted to collide these alpha particles with gold atoms and see what happens. And the vast, vast, vast majority of them just flew on through unbothered. This little ring on the outside is a detector, and it glows when these alpha particles hit it, and so they could see where the alpha particles hit. The vast majority of the alpha particles went right through the atoms. That told them that atoms were mostly empty space. They shot right through the gold foil, didn't touch anything. A few of them were deflected lightly, and so they'd go off at an angle somewhere, not straight through. And then, extremely rarely, one would be scattered backwards. And so what that told them was that the nuclei aren't spread out, but that the mass of an atom is compact in its center, or in somewhere inside. It's very compact. Otherwise, these guys wouldn't be bounced back. Alpha particles, they knew already, were very dense and tiny compared to an atom, and yet they still got repelled by this. They thought it'd be like shooting a bullet through bread. And you wouldn't expect a bullet shot through bread to come bouncing back in the backward direction, or even really to be deflected very much. And so they were surprised by this result, and that let them know that atoms were not sort of the mass in an atom, if you look at a water droplet, you might think that the mass in a water droplet is uniformly distributed through the water droplet, and it is. But if you get all the way down to an atom, no longer is it like a water droplet. It's most of an atom is empty space, and there's a teeny tiny nucleus in it that has most of the mass, and the electrons are kind of orbiting around that, kind of occupying its size. As you can kind of think of it like a solar system, which is mostly empty space, but all the mass, or 99.9% of the mass of the solar system, is in the sun. It's in the center of the solar system. It's not in the space around it. Just a tiny, all the planets in the solar system are about 1/10% or 0.2% of the mass. The sun has all of it, and it's similar in a nucleus. It's got the vast majority of the mass is in this tiny space in the center of an atom. Oops. And so this is just another drawing. The alpha particles are deflected only when they hit a nucleus head-on, which is very rare because the nucleus is very small compared to the rest of the atom. And so Rutherford's conclusions were the volume occupied by an atom must consist of a large amount of empty space. A small, relatively heavy, positively charged body called the nucleus must be at the center of each atom. They put it at the center because the electrons, which are negatively charged, are orbiting around it. The nucleus contains most of the atom's mass. Once again, it's like 99.8% or something like that. The nucleus contains most of the atom's mass. The negatively charged electrons surround it. They don't really orbit like planets. So they orbit like a cloud. They orbit like fleas around a hippopotamus or something. No, that's not a good example. Anyway, a giant cloud of fleas around some tiny animal. Right? A giant cloud of flies around a tiny animal. There we go. The proton is positively charged subatomic particle located in the nucleus. It carries the same charge as the electron because they have to exactly cancel because atoms are neutral. But it's positive instead of negative. The nucleus contains the majority of an atom's mass. The protons and neutrons are much heavier than the electrons. Electrons occupy almost all of the atom's volume. The diameter of an atom is about 10 to the minus 10 meters. The electrons occupy the atom's volume just by flying around, not because they're big. Right? It's like I was saying, it's a cloud of flies or something like that. They're not occupying a lot of space in and of themselves. They're just moving around. Diameter of an atom is about, so that's a 10 billionth of a meter, right? That's really tiny. The diameter of a nucleus is even 100 times smaller than that. So it's about 10 to the minus 15 meters. This is a nice illustration. If you blew the atom up to be the size of a football stadium, the nucleus would be a blueberry in the center. Something like that. That gives you an idea. And that's where the vast majority of the mass of the atom is, right, in that little blueberry in the center. So a carbon atom weighs less than 2 times 10 to the minus 26 kilograms. Electrons have a charge of, that should be negative, 1.6 times 10 to the minus 19th coulombs. So small units are needed to measure these things if we don't want to have all these giant negative exponents in here, right? So we create an atomic mass unit, which is 1.6605 times 10 to the minus 27 kilograms. And so a carbon atom has a mass of 12 of these. The number of protons in the nucleus of an atom is its atomic number. So the way we identify what element an atom is by this atomic number, the number of protons. So the atomic number is the number of protons. And we use the letter Z to represent it. I don't know where that started from. But so hydrogen has an atomic number of 1, helium has an atomic number of 2, lithium has an atomic number of 3, beryllium has an atomic number of 4, and so on. We'll work our way up the periodic table. This is the defining trait of an element. Any element with an atomic number of 6 is a carbon atom. Any with an atomic number of 8 protons is an oxygen atom. It doesn't matter how many electrons or neutrons it has. If it's got 8 protons, it's an oxygen atom. If it's got 92 protons, it's a uranium atom, and so on. A neutral atom must contain the same number of positive and negative charges. That means the number of protons equals the number of electrons. Atoms don't have to stay neutral. Those are called ions, and we'll get to that. But the atomic number, which indicates the number of protons, also indicates the number of electrons if the atom is in a neutral state, if it hasn't been ionized. The total number of protons and neutrons in an atom is called its atomic number. Its mass number. That's A. So we said the atomic number was Z. The mass number is A. And so protons plus neutrons is A. So a neutron is a neutral particle that lives inside the nucleus with the proton. It's got about the same mass as a proton. And so A is the mass number. Essentially, you can know what the mass of an atom is just by knowing the total number of protons and neutrons, because the electrons are insignificant by comparison. So if you know A and Z, you can figure out the number of protons, because Z is the number of, you can figure out the number of neutrons, because Z is the number of protons and A is neutrons plus protons, and so A minus Z is the number of neutrons. So ions, we just mentioned a minute ago, are charged atoms. When the number of protons and electrons is not equal, the atom is electrically charged and called an ion. Right? It can be a negative ion because it's carrying extra electrons. It can be a positive ion because it's carrying not enough, because it's lost some electrons. So the charge of an atom is the number of protons minus the number of electrons. Atoms acquire charge by losing and gaining electrons. An atom that gains one or more electrons will exhibit a negative charge, and it's called an anion. An atom that loses one or more electrons is positive charge, and it's called a cation. A chemical symbol is an abbreviation that we use to indicate the element. So for example, the symbol for mercury is Hg. You'll see these in the periodic table coming up. Some symbols are derived from the common name of the element. Others are abbreviations of some name in another language. Only the first letter of the symbol is capitalized. So here are a few. Iron is Fe from ferrum, lead is Pb from plumbum, magnesium is Mg, mercury is Hg, nitrogen is N. Here's some over here. Aluminum is Al, bromine is Br, calcium is Ca, gold is Au from aurum. So some have different origins. Sodium is Na from natrium. So tin is Sn from stannum. So there's some notation here, right, in the periodic table, or just notationally. We'll often, we'll put the symbol here. So this is He for helium. The mass number is here 4. The atomic number we put in the lower left. So that means there's 2 protons, and the total number of protons plus neutrons is 4. And so that means the number of neutrons is also 2, because this is neutrons plus protons, and that's protons. That means there must be 2 neutrons. And this one's in the upper right is the charge. It's got a 2 plus, and so on. So an isotope is an atom with the same atomic number as another, but a different mass number. An isotope is a different number of neutrons. The symbol for a specific isotope of any element is written by placing the mass number as a superscript to the left of the symbol. And so you can tell uh, different isotopes. This is magnesium 25, 24, 25, and 26. And so this is the mass number. And so if there are 12 protons, this one has 12 neutrons, this one has 13 neutrons, this one has 14 neutrons. They're all isotopes. Chemically, these all behave exactly like magnesium, because the neutrons don't participate in anything because they carry no charge. At least they don't participate in any chemical reactions. They would in nuclear reactions, but not in chemical reactions. And so they behave exactly like magnesium. If you got some of the stuff and did chemical reactions with it, it would be hard to tell which was which. Here's some isotopes of hydrogen. This is called protium. This is actually the most common form of hydrogen. And this is deuterium, and this is tritium. And these are their masses in atomic mass units: 1.0078, 2.0141, and 3.01605. Basically 1, 2, and 3, because this is just a proton, this is a proton and 2 neutrons, and this is a proton and neutron, this is a proton and 2 neutrons. Notice that percent natural abundance, 99.989, is the most common element of hydrogen. It's 99.989% in nature of the hydrogens you find are this kind. 0.0115% is this kind, and just trace elements of tritium. Each proton and each neutron has a mass of approximately 1 atomic mass unit. Each electron weighs far less, about a 2,000th of that. Therefore, the atomic mass of a single atom in atomic mass units is approximately equal to its mass number. However, most elements exist naturally as a mixture of 2 or more isotopes. So here's a picture of the periodic table again. It's the same periodic table we've been talking about. There's hydrogen, helium, lithium, beryllium. So in each case, the atomic number is here, and the number down here underneath it, like 6.94, is the statistical isotope mass. Right? You can see its mass number is about 7, which means it'll have 3 protons and 4 neutrons. Beryllium will have 4 protons, the upper left, and 5 neutrons, and so on. Tin, which is right here, right, it has 50 protons and 69 on average neutrons, so on. I'll post some questions on this on the PDF. So here are some questions for the end of this section. Who proposed atoms? The first people to propose atoms were the ancient Greeks, Democritus. What were Aristotle's 4 elements? These are all things we talked about. What were John Dalton's 5 postulates for his atomic theory? What did he say about compounds? How many copper atoms are there in a pre-1981 penny? So you just have to look up on the figure on that one. Dalton's atomic theory led to the law of conservation of mass. Law of definite proportions, that was from Dalton, who said that compounds come in direct definite proportions. It was a clue about the finite size of matter. There's 2 hydrogens for 1 oxygen in water, and that type of thing. What are the 3 basic components of an atom? You should be able to figure that out. What's the charge on an electron? Is it positive or negative? Where's the most mass of the atom? What's the charge on a proton? What's the charge on a neutron? Let me see if I can come over here and come down a little bit. What did J.J. Thomson discover with regard to the atom? pause this for a second. So, next set of questions, what did J.J. Thomson discover with regard to an atom? Remember, he figured out one of the subatomic particles it's made of. What did Robert Millikan do for that? What did Rutherford learn about the atom? That has to do with where the mass is distributed. What's the approximate diameter of an atom? You should be able to tell me that in meters. Compare the nucleus's size to the size of the atom. So those should be starkly different. What is an atomic mass unit? What's its value? What do we mean by the mass number of an atom? What element has a mass number of about 56? Which one has about 238? What's an ion? What's an anion? What's a cation? Which three components of atoms contributes the least to chemical reactions? You should know what the three main components of atoms are. I think I asked you that up above. What's an isotope? How do isotopes differ from one